So the first cell, I'm going to write the problem. So I designate it as a text cell. So here is the radioactive decay problem, and I'm going to write its equation. So I write fraction dy dt equals minus lambda times y, and the equations comes with the initial condition y of 0, and we said it's equal to 1. Now I write here the Euler's forward difference approximation. So it says y of I plus 1 equals y of I plus h times f of pi by I. We required the slope at the previous step. This is Euler's forward difference method, and the expression for Euler's backward difference method. So the expression is similar to this one, except for the indices. So I write here I plus 1, and for here it is also I plus 1, right? So that is the expression. And now the programming part. So we have got the expressions, and okay. So problem is the radioactive decay problem, and we will solve it using forward difference and backward difference method. So first, import the libraries numpy as np, and I will require the matplotlib laboratory, matplotlib.pyplot as plt. Right. So it is there now. In the next cell, I will write the journal function. So I write f of ty. So function f of ty is the right hand side of differential equation. So this requires the definition of lambda. I say lambda, and for this problem we set it equal to 1, the decay constant in this case, and I say the right hand side it should be equal to minus lambda times t value. Oh, sorry, minus lambda times y. The right hand side of differential equation, you may take it from the above expression. Yes, minus lambda times y. Let me correct it that this is correct, but for our notation, the notation we use in the context of numerical solution of differential equation, the notation is this one. The right hand side is equals to fty, right? So I am going to define the right hand side, the function, so lambda y, and then in Python I can say return value, and that's it. So the function has been defined. This is the right hand side, so it is now included in our system. Now the next part of the cell, well, I should better write comment here, define the function. Now in the next cell, At first, I write the algorithmic implementation. This is the part of algorithm implementation, right? So in this demonstration, I'm going to write it in the form of a function, right? So I write here define, I say Euler forward difference. What should be the inputs? A differential equation is defined with the function f, right? Then there should be the initial condition. I say the initial condition would be y naught. Then there should be the span in which you want to evaluate the solution, right? Solution domain. In this case, the time span from 0 to infinity or 10 or 2, 20. So I say the time span. So I say t span. Time span and the step size h, right? So these should be specified by the user. So good practice. So I define all the things. F is the function. Y naught refers to the initial condition. Then T span, it should be the solution domain, right? So maybe defined as the limits AB, right? So it should be a list or it should be an array. T span, and then what is final thing is the H, which is the step size, right? So these are the comments. I have defined the variables. What else is required is the solution variables, right? T span is the only the endpoints. We required the time and the number of points, right? With reference to step size. So with H and T span. Okay. So I say let's define n, the number of points. So I define it like T span 1 minus T span 0. So B minus A is like B minus A divided by H. So these are going to be the number of points. And then let's define the time T variable vector. So I define it numpy A range, start from T span. Let's simplify it for first time. Let's keep it simple. Y naught. A is the starting point, B is the end point. Okay. So instead of T span, let's say A starting point, and let's define B as the end point. End point of the solution domain. So I can simplify it as B minus A divided by H. This will give us the number of intervals, right? So I say A range from A to B plus H is a step size of H. So time domain is going to be created. So this is T span, T time. We also require the solution vector. So this should be defined at every point of T. So solution vector Y will be numpy zeros, and I would say it should be from zeros. There should be n zeros of float type. So a vector of time is created and a vector for Y has been created. Now the first value of Y y of 0, this should be the initial condition, the starting point. So set the initial condition. Right? Now, how to get the next value? So we can write here for I in range. So we write it from to n minus 1, right? We can say y of I plus 1 equals y of I plus h times f of ti yi. So please appreciate the similarity between the algorithm that we write, algorithmic expression, and the programming expression, right? So see, yi plus 1 is equal to yi plus h times f of ti yi. So it will do the job for all. This is the end of this for loop. And what values we would like to return? We would like to return the time vector and the vector y. That's it. That's it. So that is the end of Euler's forward function. Now it's time to use it, right? I defined the n value. If you observe the output variables, so these are the output variables. Let me write here output variables. So let's see whether there are errors or not. And now it's time to use this function with the values, right? The function requires, let me pick this up to identify that these are the required things. Okay, f has been defined above. We have to define y naught. So let's define y naught value. So y naught equals the initial condition. It was set equal to 1. So I'm writing it 1. Then a b. So I define a equals 0, the starting point. B equals say 10. And I have to define h. So I take h equals 0.2, right? These are the values. Now I define solution, or I can simply write Euler forward difference f y naught a b h. That's it. See the answer. Okay. Some error has been returned. Float object cannot be interpreted as integer by zeros and is it really the error or not? Still there is error. H equals 0.2. Numpy zeros. A b plus h. A b plus h. So I have said this expression equals to integer, and I hope now this will be settled. Yes. So the expression b minus a over h, it should be converted to integer. Now, whether something has been returned or not, let's see. Okay, so we have got the answers, right? So two arrays have been generated. So how to get that? Actually, this is a special type of variable in Python which is known as tuple. So I say, for example, solution is equal to Euler. Now to print the time variable. So I can say, let's see the plot. Call it directly in the plot. I say plt dot plot solution, the first vector and the second vector, and plot it as red circle. Okay, the language is sensitive, so we have to apply it carefully. Okay. Oh, not the 2. It should be 1. There are 2 vectors in Python. The indices run from 0 and less than. Okay. plt dot plot solution 1, solution 2 are of 0. Lambda value was 1. Plot. Let me see whether I'm picking the values correctly or not. Yes, this is fine. Yes, they are correct. Okay, the other check, by size of solution 0 and numpy size of solution 1. So there is the inconsistency, right? So somehow I have reduced the dimension of y0. Okay. Range. Now let's define n here. N equals numpy size of, right? So this will be definitely integer. Again, run this one. Okay, this is correct. Now this is correct. Then now let's check the sizes. Yes, this is fine now. And now the plot. Behold, this is the most critical stage. I have eliminated all of the errors. I guess so. And Python plot is now being generated. Here it is. But we really want to check it against the analytical one. So let's see how I do it. So before this one, I write here a statement by exact equals exact solution of the radioactive decay equation equals y naught times numpy e raised to the power minus lambda, and or minus lambda is equal to -1 times. That's it. And now I plot with the exact value. I say plot. Okay, in the same line I can write solution 0, the time vector times y exact, and plot it as a blue line, and the rest with the other attribute as red dots, and I add legend. You know why this is important, right? So it is the exact analytical, and the other is Euler's forward difference solution. I can set X label. X label here is time, and Y label equals Y of t. Okay, that's fine. Okay. There is error. Okay, it should be, well, time t variable is used inside the function. So outside it is the variable solution 0. Yes, I have used t in the function. So this is the analytical and Euler's forward difference method, right? Euler's forward difference method. Now I'm going to convert it. See the expression for Euler's backward difference method. So it is yi plus 1 equals yi plus f of ti plus 1 yi plus 1, right? So yi plus 1 is required. So I use the Euler's forward difference expression as the predictor one. So I have the yi plus 1 value here. This is the function. So this is the yi plus 1 value. So I say this is a guess value, right? And now in the next line, say in this line, this is the predicted value of y. Predicted value of y I plus 1. So now I use this value as a corrector. So I write yi plus h times f of t I plus 1 yi plus 1. Get the value of yi plus 1 from the current step. So this expression now serves as the corrector. Please pardon the change of the name. We can do it. Make it backward difference, I say it is BD. The rest of the structure is the same. And here, instead of FD, I'm now going to use BD. So before running it, please we'll look at the solution, where the beads are slightly below the blue line. And now let's run everything, all the cells. Right? Okay, not FD. Now I require the expression for BD. So now the computations are slightly different. So y exact and the solution. So you may notice that now the beads of numerical solution are slightly above the analytical solution, right? So Euler's forward and backward difference method, one predicts slightly overestimate and the other backward difference computes slightly underestimate. So with this demonstration, I hope you will never ever falter with the forward difference and backward difference methods.